Hey guys, I'm Jed. Welcome back to my LeetCode Review One Thing vlog on the 433rd problem, minimum genetic mutation. A gene string can be represented by an 8-character long string with choices from A, C, G, and T. Suppose we need to investigate a mutation from a gene string start gene to a gene string end gene, where one mutation is defined as one single character changed in a gene string. For example, AACCGGTT transforms to AACCGGTA is one mutation because the last character T changed to A. And there is also a gene bank that records all valid gene mutations. A gene must be in the bank to make it a valid gene string. We are given two string strings, start gene and end gene, and a gene bank called bank. We need to return the minimum number of mutations needed to mutate from start gene to end gene. If there's no such a mutation, we'll return -1. Note that the starting point is assumed to be valid, so it might not be included in the bank. And let's see the example 2 here. We got start gene, end gene, and bank. First, AACCGGTT needs transform to AACCGGTA, so the last character T changed to A. Then we'll change it to the AAACGGTA, which means the third character C changed to A, and that's the end gene. And the minimum path is about 2 steps, so our output is 2. Then let's get started with our intuition to solve this problem. Intuition. When we look at this problem, we could recognize it as a shortest path problem. Each gene string represents a node, and there is an age between 2 genes if they differ by only 1 character. What we need to find is the shortest path from the start gene to the end gene, going through only 1 valid mutations in the bank. We can think of several solutions, from less optimal to more optimal. Firstly, we could use depth first search with backchecking to check all the possible mutation paths. But this is very inefficient because we have to check all the possibilities. Depth first search. Secondly, we may use breadth first search to find the shortest path, or we'll use the bidirectional breadth first search, which searches from both start and end simultaneously to reduce the search space. So the second approach is breadth first search and bidirectional breadth first search. And let's start with the standard breadth first search. The main idea is to use breadth first search to explore all the possible valid mutations, level by level, until we reach the end gene or checked all the possibilities to return -1. In the code, we start by creating a hash set variables because we need to convert the bank into a hash set for big O of 1 lookups, which will make it efficient to check if a mutation is valid. Let's say set of string called bank set. Bank set gets a new empty hash set. And we need to initialize it with arrays.asList of bank. Next, we need to check if the target gene isn't in the bank or not. We can't reach it with valid mutations. So we immediately return -1 to indicate that it is impossible. If not symbol bank state dot contains of n gene. If so, we will return -1 because it is impossible. Otherwise, we'll create a character arrays containing 4 characters in a gene to generate all possible mutations. And the 4 characters are A, C, G, T in this problem. Let's declare a character array called valid characters gets A, C, G, and T. After that, we need to create another queue to perform our breadth-first search, starting with the start gene. So queue of string called queue gets a new linked list, and we need to add a start gene into the queue.author of the start gene. And we need to check genes that we've already visited, so we can avoid cycles and redundant processing. So we'll create another set of string called visited gets a new hash set, and we need to add the start gene into the visited hash set. Visited dot add of start gene. Following that, we declare a variable to check how many mutations we've made so far. Integer mutations started at 0. Now, we need to begin our breadth-first search with a while loop. While not logical symbol q dot is empty. So we'll continue the while loop until the queue is empty. For each iteration inside the while loop, we need to process all genes at the current mutation level together. Firstly, we need to get the static size of the queue before modifying it. Let's say integer level size gets queue.size. Secondly, we process all genes at the current level with another for loop. Let's say integer for integer I started at 0 when I is less than level size. We'll increment I after each iteration. Inside the inner for loop, we need to get the current gene that we are examining. String current gene gets q.poll. Next, if we've reached our target, we will return the current mutation count. But we have to check it. If current gene dot equals of n gene. If so, we'll return the mutation so far. Or we'll check changing each position in the current gene by transforming the current gene string to character arrays at first. We'll declare a character array called gene array. Gets current gene dot to character array. Then we use a for loop to iterate all the characters in the current gene. For integer j started at 0, when j is less than gene array dot length, we'll increment j after each iteration. For each iteration, first we need to save the original character so we can restore it later. We'll declare a character called original character gets gene array of j. Now we create another enhanced for loop to check each possible character at the current position. And code is for character C in valid characters. For each valid character, we'll skip it if it is the same character, which means it's not a mutation. If C equals original character, we'll skip it. Continue. Otherwise, we apply the mutation and get the mutated gene string. Gene array of j gets C string mutated gene gets new string of gene array. After that, we'll check if this mutation is valid and not visited. If backstate dot contains of mutated gene and not symbol visited dot contains of mutated gene. If so, we add it to our queue for further explorations. Queue.offer of mutated gene. And we also have to mark it as visited to avoid processing again. And the code is visited dot add of mutated gene. That's it. Out of the enhanced for loop, we need to restore the original character for the next iteration. So the code is gene array of j gets original character. After processing all genes at the current level, we need to increment the mutation count. Mutations increment. Finally, if we've checked all the possibilities without finding the end gene, we'll return -1 because there is no valid mutation path. Alright, that's all of the code. Let's submit the code and check if our solution passes all test cases. Yes, our code got accepted. Now, let's analyze the time and space complexity. So, before we analyze it, we will declare several letters. For example, let's say N is the number of genes in the bank, is the number of genes in the bank. And L is the length of each gene, which is 8 here. So for the time complexity and for each gene, we try to mutate each position with 3 other characters. And in the worst case, we might examine all the genes in the bank. So the time complexity, it is big O of N times L times 4. And for the space complexity, we store the bank in a hash set. And the Q and the velocity state could contain at most N genes. So the overall space complexity is big O of N. And this is the end of my LeetCode review vlog on this problem, minimum genetic mutation. And I highly recommend you guys to visit my online GitHub page here, which contains all the problem description, incubation and main idea, solutions with very detailed comments, and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the codes and notes to build this online GitHub page. And I'll put those 2 links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.